What if I told you there's an ocean above your head? A vast, invisible sea that's just as alive, just as dynamic as the waters below. In this Science for Sleeping video, we'll explore the gentle currents and towering waves of our atmosphere, drifting through its layers to uncover the secrets behind the weather we see every day. From the serene rise of warm air to the breathtaking power of thunderstorms. This journey will help you see the sky as you've never seen it before. The atmosphere, an ocean without waves. Imagine an ocean, but one you can't see, touch, or hear. No rippling waves, no salt-sprayed shores, yet it's teeming with motion and brimming with life-giving energy. This ocean wraps around the entire Earth, pressing gently against your skin every moment of the day. You've been living within it all your life, the atmosphere. Unlike the familiar seas and rivers below, this invisible ocean surrounds us entirely, stretching from the ground far upward, where it eventually fades into the endless vacuum of space. But even in its silence and invisibility, this atmospheric ocean is anything but still. Most of the time, it feels like nothing at all. You might step outside and feel a breeze, or during a storm, you might hear the howling anger of rushing air. But most of the time, it's easy to forget the atmosphere is even there. Yet it's moving constantly, cycling through endless patterns and changes. This ocean above carries with it the invisible substance of life itself. It's made primarily of nitrogen, around 78% of it to be exact, which plants use to build the compounds they need to grow. And then there's oxygen, making up about 21%, fueling you with each breath you take. The rest, just a tiny sliver, consists of argon, carbon dioxide, and water vapor. The last one, that minuscule trace of water vapor, is what transforms this mixture into the stage for weather. Without that tiny fraction, there would be no floating clouds above us, no shimmering rains, no icy snowstorms. The smallest pieces sometimes have the largest roles. What keeps this delicate mix intact and wrapped around Earth is gravity itself. Just like the way the oceans below stay drawn to the planet's surface, the atmosphere clings tightly to Earth, held in place by gravity's pull. It's the reason air doesn't simply drift off into space, and it's also why weather exists at all. Without the force of gravity binding air close to the surface, there would be no pressure, no temperature differences, no wind brushing through the trees. Gravity turns this mixture of gases into a contained system, a world where every breeze and storm becomes a part of its unbroken dance. But if the air has always felt so still and empty to you, it's likely because much of its complexity is hidden in its layers, stacked high above like the floors of a building. The atmosphere isn't a single, uniform space. It's divided into unique sections, each performing a different role. Much like an orchestra of unseen instruments playing together. Closer to the ground, the air is thicker, heavier, and jam-packed with movement. This is where your weather comes to life. But as you climb higher and higher, the air changes, thinning out, growing colder or warmer in surprising patterns, until it becomes something so sparse it would hardly seem like air at all. Every layer has its own purpose. Some shield us from the harsh energies of space, while others act as staging grounds for the storms and calm skies we experience below. Consider this: the atmosphere isn't just a blanket draped over the Earth. It's a living system, a constant balancing act. At times, its role feels almost poetic. It shields us with its strength, absorbing dangerous radiation from the sun and burning up meteors before they touch the ground. And yet, it's fragile enough that we can walk through it, barely noticing it's there. It sustains us, carrying oxygen to our lungs and rain to our crops, while also acting as a restless performer, presenting us with sunsets, whispering winds, and sudden lightning storms. It is both the protector of life, as we know it, and the thrilling arena where weather takes center stage. When you look at the sky right now, it might seem endless, stretching in every direction like a blue canvas. But the truth is, most of the atmosphere, the air you're breathing this very second, is packed tightly into just a thin layer hugging the earth. The higher you go, the more this ocean thins, its density trickling away until there's almost nothing left. It's incredible to think that something as massive and vital as the sky essentially balances on this narrow layer, an envelope no thicker than the skin of an apple compared to the earth itself. But what would happen if you could journey upward through this invisible ocean? What would it feel like to drift beyond the familiar ground and rise through its layers? As we move forward, let's gently explore what makes each part of this atmospheric ocean unique, from the birthplace of weather to the distant reaches where space begins to whisper its presence. Drifting upward, the atmosphere's layers. What if you could float upward, leaving the solid ground behind and rise quietly through the atmosphere's layers? It might feel like slipping through invisible veils, each one revealing something new. As you ascend, the world below you would change, but so would the very air around you, the temperature, the pressure, even the way life and light behave. The atmosphere isn't just an indistinct sea of gases. It's a finely organized system, with each layer playing its part to keep our planet alive and in balance. Let's rise through these layers together and see what makes each one so essential. The journey would begin in the troposphere, the lowest and most familiar layer of the atmosphere. It's where all the action happens, at least the action we see and feel every day. The troposphere is the weather layer. It's where clouds form, where winds swirl, and where moisture in the air gathers into rain, snow, or even dramatic storms. This is the layer where life lives and breathes. But as you rise higher through it, you'd start to notice changes. The air gets thinner, the temperature cools, and you'd feel the pressure of the atmosphere gradually easing its grip. Although this layer only extends about 7 to 10 miles above the ground, it holds about 80% of the atmosphere's mass, making it dense, rich, and bustling with movement. If you were able to keep going, to float past the top of the troposphere, you would cross into the stratosphere. This is where the air starts to feel calmer. No weather happens here. In fact, this layer sits above the turbulence of storms and winds, providing a smooth, still region. But even in its calm, the stratosphere is hard at work. This is where the ozone layer lives, a thin band of oxygen molecules that absorb much of the sun's ultraviolet radiation. Without this protective shield, life on Earth would be exposed to far more harmful UV rays, making it challenging for many organisms to survive. It's fascinating to think that an invisible layer of air, so far above us, is silently blocking waves of hazardous energy from reaching the surface. Also, unlike in the troposphere where things cool as you go higher, the stratosphere warms slightly as you rise, an unexpected effect of the ozone layer doing its job. Beyond the stratosphere, you'd enter the mesosphere, a layer that often gets overlooked because it doesn't seem as action-packed. But the mesosphere is crucial in its own strange way. Temperatures plunge here, and it's home to some of the coldest spots in the atmosphere. It's also the layer where meteors burn up as they streak toward Earth, leaving behind bright flashes of light we call shooting stars. Imagine this. Every time you've looked up and wished on a falling star, you were seeing the mesosphere at work. The friction created as meteoroids slam into the sparse air particles here causes them to burn brilliantly, keeping us safe from impacts. It's a layer that quietly protects us while putting on a show for anyone paying attention. Above the mesosphere is the thermosphere, and it might feel like you've stepped into an entirely different world. This layer is where the atmosphere starts to merge with the edge of space, and everything begins to feel much more extreme. Temperatures here can soar to thousands of degrees Fahrenheit due to the absorption of high-energy solar radiation. However, it wouldn't feel hot to you, not in the way you're used to, because the air is so thin that there are very few molecules to transfer heat to your skin. The thermosphere is also where the magical flicker of the auroras occurs. The northern and southern lights, created as solar particles collide with gases in the atmosphere. It's not just a scientific phenomenon, it's nature's quiet masterpiece, painted across the heavens. Finally, at the edge of everything, there's the exosphere. It's not so much a clear boundary as it is a gradual fading away of air, thinning into the vacuum of space. In this final layer, the molecules of the atmosphere are so sparse, they can travel for miles without colliding into each other. Satellites glide here, orbiting quietly, and this is where Earth's atmosphere ceases to behave like an ocean of air and starts to resemble the vast emptiness of space. It's a humbling thought that our entire planet's air supply thins down to almost nothing within just a few hundred miles of the surface. Each layer, from the troposphere to the exosphere, carries a unique role in keeping our planet habitable. From providing the air we breathe, to shielding us from deadly radiation, to protecting us from meteors, the atmosphere is incredibly complex. And yet, it functions perfectly as a whole, like finely tuned machinery. Every piece depends on the others to keep it all running smoothly. It's easy to take this complexity for granted, to assume the air above us is just empty space, but it's far from that. It's a rich, layered system that not only surrounds us, but sustains us. As we descend again in our thoughts, back into the troposphere, think about how much is happening in just this one layer. The winds, the clouds, and the signs of life all around you. The troposphere is where air is thickest, where water vapor can condense, and where these dynamic processes create the weather we know so well. But what drives its movements? What causes the winds to blow or the clouds to form? To understand the heartbeat of this layer, we need to explore how temperature, pressure, and moisture interact, and the intricate forces that set the atmosphere into motion. The troposphere, where weather comes alive. The troposphere may feel like the quietest part of the atmosphere to us. After all, it's where we live, breathe, and go about our daily routines. But it's also where the most extraordinary processes of weather unfold, every single moment. Despite spanning just a few miles above the Earth's surface, the troposphere holds nearly everything we associate with weather, from gentle breezes to ferocious thunderstorms, and from misty clouds to cascading rain. It's a compact yet vibrant layer, bursting with activity that shapes the world we see, feel, and experience every day. What makes the troposphere so special is its density. Compared to the layers of the atmosphere above it, the air in the troposphere is far thicker and heavier, meaning most of the atmosphere's mass is packed tightly into this one zone. To imagine it, think of Earth like an apple. The troposphere is like the ultra-thin layer of skin around that apple. It's incredibly small on a planetary scale, yet vital to almost everything happening at its surface. This density is what makes the troposphere unique, and it creates the ideal conditions for weather to come alive. Warm air, cool air, and water vapor swirl together here in an unending dance, shaping clouds, rain, storms, and even snow. But what really sets this layer apart is its ability to hold water vapor. Although water vapor makes up only a tiny fraction of the air around us, it has an outsized role in creating the weather. Why? Warm air has a remarkable capacity to hold moisture. Picture it like a sponge, soaking up water as it rises. As warm, humid air drifts upward in the troposphere, something fascinating happens. The air starts to cool. And when it cools enough, reaching a point called the dew point, the water vapor it's holding can no longer remain in its invisible vapor form. It condenses, turning into tiny droplets of liquid water, or in colder conditions, into ice crystals. These tiny droplets gather together, forming what we recognize as clouds. What feels like a simple, everyday view, a cloud drifting across the sky, is actually the result of countless water molecules banding together high above us, and it all starts with the dynamics of the troposphere. This rising and cooling of air doesn't happen randomly, though. It's part of a larger pattern governed by temperature and pressure. Warm air, because it's less dense, naturally rises. Cold air, being heavier, naturally sinks. This simple relationship creates a constant flow of movement, what we call convection currents. These currents are like invisible conveyor belts, moving air and moisture around the troposphere, redistributing heat and energy in the process. It's this ceaseless movement that fuels weather. Without it, the sky would be still and lifeless, a stagnant expanse with no clouds and no rain. But instead, the troposphere is alive with motion, full of rising warmth, sinking cold, and the endless exchange of energy. While this constant churning creates balance, it also creates chaos. Temperature, pressure, and moisture interact in ever-changing ways, triggering different types of weather. For example, if warm, moist air rises rapidly, it can lead to towering thunderclouds capable of producing dramatic storms. On the other hand, gentle, slow-moving air might only result in soft clouds and a mild drizzle. The interplay of these elements is ongoing and dynamic, which is why weather can feel so unpredictable. One day might bring clear skies and sunshine, while the next could be filled with gusty winds and rain. If you were to climb upward through the troposphere, you'd notice something curious. The air steadily becomes thinner and the temperature drops. This decrease in temperature is known as the environmental lapse rate, and it's the reason mountaintops are often colder and less hospitable than the valleys below. The higher you go, the farther away you are from the heat radiating from the Earth's surface, which is the primary energy source for the troposphere. This temperature difference is another factor that drives the movement of air. Heated air near the ground rises, while colder air from above descends, creating a constant cycle that powers weather systems. Another key player in this story is air pressure. Since the troposphere contains the thickest, heaviest air of all the atmosphere's layers, the pressure is highest here at the surface. As you climb higher, that pressure drops, almost as if the weight of the air above you is slowly being lifted away. This shift in pressure also has an important influence on weather. When areas of high pressure form, they bring calm, clear skies, as the sinking air suppresses cloud formation. But when low-pressure zones develop, they allow warm air to rise freely, often leading to cloudy, stormy conditions. The constant tug-of-war between these pressure zones adds yet another layer of complexity to the troposphere and the weather it produces. One of the most amazing things about the troposphere is how seamlessly it balances its chaos. While it might look random on the surface, there's an underlying order to it all. The distribution of heat, the movement of air, and the way clouds form and rain falls all tie back to the natural rules of temperature and pressure. In this way, the troposphere acts like a self-regulating system, ensuring no one area becomes too hot, too cold, too dry, or too wet for too long. It's a perfect example of nature working toward balance, even through endless, swirling motion. And yet, as intricate as the troposphere may seem, it's really just the first layer of our atmosphere, the lowest point in a much larger system. Weather takes shape here, but it's influenced by forces that extend far beyond. From the rotation of the Earth to the movement of the sun's energy across the planet. These larger influences help direct the winds, pressure zones, and temperature changes that the troposphere responds to. If the troposphere is the stage where weather unfolds, then the forces driving air movement and pressure changes are the unseen hands guiding the performance. So, the next time you step outside and feel a breeze brushing your face, or see rain falling from a low-hanging cloud, remember the complexity behind what you're experiencing. It all begins here, in this thin and bustling layer, packed with life, energy, and motion. The troposphere might seem fleeting and ordinary, but it's anything but. It's the reason we have clouds to watch, storms to marvel at, and the delicate patterns of weather that define our days. But what exactly is it that pushes the air to move in such intricate ways, creating breezes, gusts, and winds that never settle down? To understand that, we'll need to explore the invisible forces at play, driving every whisper of movement in the air and every swirl of clouds in the sky. The dance of air, temperature, pressure, and wind. Air is in constant motion. Even on the stillest days, when the trees barely sway and the clouds seem frozen in place, the ever-present movement of air is quietly shaping the atmosphere around us. But why? What drives the air's endless, flowing dance across skies, cities, and oceans? To answer that question, it helps to think of air not as an invisible, weightless substance, but as a fluid, one that's constantly responding to tiny shifts in temperature and pressure. These shifts, as simple as they sound, are what set the whole system into motion. Warm air is lighter. You might not think of air as having weight, but every cubic inch of it presses down with its own tiny force. Warm air, however, is less dense. It spreads out, becoming thinner, almost like a balloon that's just been filled. The sun heats the earth unevenly, warming some places more than others. So as certain pockets of air get warmer, they rise. Cold air does the opposite. It's heavier, thicker, and sinks lower, pushing the lighter air above it. This fundamental principle, warm air rises, cold air sinks, sounds simple, and yet it's the heartbeat of everything that happens in our atmosphere. These small differences, these tiny movements, begin to stack up. Take a moment to imagine a pot of water heating on a stove. At first, the water is still. Then, as the bottom of the pot warms up, the heated water starts to rise, replaced by cooler water, sinking down to take its place. This cycle repeats over and over, creating swirling, looping motions, convection. The same thing is happening all around you, just on a much grander scale. As sunlight hits the ground, the air above it warms and begins to lift. Up it goes, while cooler air swoops in to replace it, creating invisible cycles that roam across the earth. But here's where things get even more interesting. It's not just the simple rising and falling of air that drives this endless motion. It's also the uneven heating of the earth. The sun doesn't shine evenly across the planet. Near the equator, sunlight strikes more directly, delivering far more energy than at the poles, where the sun's rays approach at a slant. This creates an enormous temperature imbalance, hot rising air near the equator and much cooler sinking air near the poles. As the warm air rises, it creates an area of low pressure near the Earth's surface. Cooler, denser air from areas of higher pressure rushes in to take its place. This large-scale movement creates convection cells, enormous loops of moving air that carry warm energy away from the equator and redistribute it toward the colder regions at the poles. These convection cells are like giant atmospheric gears, but they're not the only forces at play. Another key factor in the movement of air is pressure. Atmospheric pressure is essentially the weight of the air above you. At sea level, that weight adds up to about 14 pounds per square inch, gentle enough to go unnoticed, but always there, pressing down on every surface. But pressure doesn't stay consistent. It varies from place to place, largely driven by temperature. Warm air, as it rises, creates areas of low pressure. Cold air. That's why high and low pressure systems are so central to weather. High pressure systems are marked by sinking air. As air sinks, it becomes warmer and drier, preventing clouds from forming. That's why high-pressure days often bring calm weather and clear blue skies. Low-pressure systems, on the other hand, are created by rising air. As the air lifts, it cools, allowing moisture to condense into clouds. These systems have a reputation for stirring up more dramatic weather, cloudy days, rainy afternoons, and even powerful storms. It all depends on how strong the contrast between high and low pressure is and how much moisture is hanging in the air. Wind follows these pressure differences like a river flowing downhill. It rushes from areas of high pressure to low pressure, seeking balance in the atmosphere. On a small scale, this gives us the breezes we feel in our neighborhoods. But on a larger scale, it contributes to enormous wind systems that stretch across continents and oceans. The interplay of warm and cold air, rising and sinking, is constantly at work, creating a system that's never quite at rest. To think of it another way, wind and weather are nature's way of maintaining balance. The Earth heats unevenly, creating areas of excess energy in some places and deficits in others. These differences can't stay that way forever. The atmosphere is always trying to even things out, moving energy from where there's too much to where there's not enough. Wind is the result of this constant pursuit of equilibrium, a dynamic balancing act that keeps the system in motion. If we were to follow the wind's movement even further, we'd start to notice something strange. While air naturally flows from high to low pressure, the paths it takes aren't always straight. Instead, wind curves and twists as it travels. This isn't a random quirk. It's the result of an invisible force created by Earth's rotation. Known as the Coriolis effect, this phenomenon adds a fascinating layer of complexity to the movement of air. In the northern hemisphere, the Coriolis effect causes winds to curve to the right, while in the southern hemisphere, they curve to the left. This gentle tug influences everything from small breezes to massive wind systems, giving the atmosphere its distinct patterns and shapes. The Coriolis effect is why large-scale winds, like the trade winds and jet streams, seem to flow along curved paths. It's also why cyclones spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. This rotational twist takes the simple idea of wind, air moving from high pressure to low pressure, and layers on an added complexity, shaping global weather patterns in ways that are anything but straightforward. When you step outside to feel the wind on your face, it may seem like a simple thing. But pause for a moment. to consider what you're really experiencing. Each breeze is a result of tremendous forces at work. The rise and fall of warm and cool air, the pull of pressure systems trying to equalize, and even the gentle nudge of the earth spinning beneath your feet. Wind may feel like the lightest thing in the world, but its movements are driven by principles so fundamental they shape our planet's entire climate. And yet, there's even more to the wind's journey. The Coriolis effect doesn't just bend the wind. It creates patterns that span the entire globe. These patterns flow into each other, linking every region on Earth into a single connected system. From the steady trade winds that propelled ancient explorers, to the roaring jet streams high above, to the polar easterlies carrying icy air southward, these distinct winds are all part of the same harmonious dance. They reveal how the atmosphere, for all its chaos, moves with an underlying rhythm. But while the Coriolis effect explains why wind curves, it doesn't tell the whole story of the atmosphere's complexity. To understand the full picture, we need to add one more element to the mix, something hidden yet vital. It's a substance you can't see, but one that fuels some of the most dramatic weather events on Earth: water vapor. What role does this invisible, weightless gas play in storms, clouds, and even the air we breathe? As the wind continues its journey, it carries this hidden force wherever it flows. Let's follow it to see what happens next. The invisible force that curves the wind. Imagine standing in a wide open field on a windy day, feeling the air brush against your skin. You might think the wind would move in straight lines, taking the shortest path between 2 points. But if you could track its full motion, you'd see it curve or twist slightly along the way. This curve isn't random. It's shaped by a force you can't see or feel: the Coriolis effect. Born from the Earth's rotation, this invisible push is why the wind rarely flows as a direct line from here to there. The Coriolis effect starts with a simple reality: the Earth spins. But the planet doesn't rotate as a solid, uniform disk. Different parts move at different speeds. At the equator, the Earth's surface. In the northern hemisphere, the Coriolis effect causes this curve to bend to the right. In the southern hemisphere, the same effect causes air to curve to the left. It's not as dramatic as a sharp turn. The curve is subtle, almost delicate. But over long distances and enough time, it reshapes the air's journey. Winds blowing across continents or even oceans bend in patterns that wouldn't exist if the Earth didn't spin. This seemingly small effect has a huge influence. It's what gives the global wind systems their shape and structure. Take the trade winds, for example. These reliable, steady breezes blow from east to west near the equator, and they've been a critical part of history. For centuries, sailors depended on them to move goods across vast oceans. Without the Coriolis effect, these winds would likely blow directly toward the equator from higher latitudes instead of curving in their characteristic paths. Above the trade winds, in the mid-latitudes, you'll find the westerlies. These winds, shaped by yet another interaction between air pressure and the Coriolis effect, blow from west to east. They're responsible for moving weather systems across much of North America and Europe. And near the poles, the polar easterlies complete the system, blowing icy, dry air from east to west. Together, these patterns form the atmospheric highways that transport air, moisture, and energy across the globe in predictable flows. The Coriolis effect doesn't just organize the winds. It also leaves its signature on much larger weather events. Hurricanes, for instance, owe their remarkable spinning shape to this invisible force. These massive storms form near the equator, where warm, moist air rises quickly and spirals in toward a central low-pressure area. As the air rushes inward, the Coriolis effect gives it a twist, causing the storm to spin. In the northern hemisphere, hurricanes rotate counterclockwise. In the southern hemisphere, their rotation flips, swirling clockwise instead. The same principle applies to smaller systems like cyclones and typhoons. The Coriolis effect doesn't create these storms, but it helps organize their chaotic energy into the distinctive, swirling structures we associate with extreme weather. You might wonder why this effect is noticeable in huge systems like hurricanes, yet doesn't seem to impact your backyard weather in the same way. The answer lies in scale. The Coriolis effect becomes stronger the larger the system, and the farther it stretches over the Earth's surface. For small-scale winds, like those blowing through a park or city street, the effect is too weak to make much of a difference. But when you're dealing with large air masses traveling hundreds or thousands of miles, that gentle nudge from Earth's rotation becomes significant, shaping everything from wind direction to pressure flows. Even jet streams, the high-speed rivers of air that run through the upper layers of the troposphere, are influenced by the Coriolis effect. These ribbons of wind form along sharp boundaries between cold and warm air masses, like those between polar and mid-latitude regions. As these temperature contrasts cause air to rush from high pressure to low pressure, the Coriolis effect kicks in, bending the jet streams into curving, meandering paths that circle the globe. These jet streams play a critical role in steering storm systems, influencing seasonal weather patterns, and even affecting how long it takes for your next flight to cross the Atlantic. The strength of the Coriolis effect isn't uniform everywhere. It's greatest at the poles and weakest at the equator. Near the equator, the rapid rotation of the Earth cancels out much of the effect, so winds there tend to flow more directly. This is why tropical storms like hurricanes don't form right on the equator. They would lack the spin needed to organize into something so powerful. But as soon as these storms drift away from the equator, even by a few degrees of latitude, the Coriolis effect engages, setting their rotation into motion. The relationship between the Coriolis effect and the wind isn't just about bending or curving. It's part of a much larger system that ties together pressure, temperature, and motion across the atmosphere. Wind exists because of differences in pressure, caused by uneven heating from the sun, but the Coriolis effect ensures that wind doesn't travel in predictable, straight lines. By shaping and redirecting these movements, it creates the swirling patterns we see in satellite images and the curved paths that underpin global weather systems. It's a subtle force, but without it, the atmosphere would lose much of its structure and order. Of course, wind isn't the only thing shaped by the Coriolis effect. Ocean currents feel its influence as well. When surface winds push water across the seas, they carry the rotational tug of the Earth with them. This creates massive, circular patterns of ocean movement, known as gyres. These gyres, powered in part by the Coriolis effect, transport heat, nutrients, and energy across the planet, linking the atmosphere and oceans in a single system. It's a reminder that the forces shaping the air are also deeply connected to the movement of water below. Understanding the Coriolis effect isn't just about satisfying curiosity, though it is fascinating to imagine an invisible force bending the movements of an entire planet's atmosphere. This effect plays a direct role in the forecasts we all rely on, from tracking hurricanes to predicting seasonal winds. Meteorologists use the Coriolis effect to model storm paths and identify areas at risk of extreme weather. It helps us understand why storms curve off course, or why weather patterns linger in one area longer than expected. Without incorporating this underlying force, our understanding of weather would be incomplete. As remarkable as the Coriolis effect is, it's only one piece of the intricate puzzle of weather. Wind might be the messenger of temperature and pressure changes, but another invisible player in the atmosphere has an even more dramatic role to play. Water vapor, though it floats silently in the air, holds the power to transform. It's the energy source behind the clouds above, the storms we watch roll in, and the rain that nourishes the ground. Let's turn now to this quiet hidden force, the engine of weather, and discover how it drives the dramatic changes we see in the sky. Water vapor, the hidden engine of weather. Even when the sky looks perfectly clear, there's something remarkable drifting through the air around you. Water vapor. You can't see it, touch it, or feel its weight. Yet it's one of the most powerful forces in the atmosphere. Water vapor is more than just invisible moisture. It's an essential part of how weather works. Without it, there would be no clouds, no rain, no thunderstorms rolling through the horizon. It's the hidden ingredient that fuels much of the activity in the sky, quietly driving some of the most dramatic processes above us. At first glance, water vapor doesn't seem very special. It makes up only a tiny fraction of the air we breathe. You're surrounded mostly by nitrogen and oxygen, but that small amount of vapor holds the key to so much of what happens in the atmosphere. What sets water vapor apart is its ability to store and release energy. As it moves through phase changes, shifting from a liquid to a gas or back again, water vapor absorbs and releases heat, acting like a kind of atmospheric engine. This process controls more than the weather. It's part of the Earth's overall system for redistributing energy. Think about how it works. When sunlight warms rivers, lakes, oceans, or even the damp soil, some of the water molecules at the surface break free and drift into the air as vapor. This is evaporation, and while it's an everyday event, it's quietly rewriting the energy of the atmosphere. The water molecules, now in vapor form, are carrying the energy they absorbed as heat from the Earth's surface. They rise into the sky, invisible but packed with potential. Warm air, as you might remember, has a higher capacity to hold water vapor. It's this detail that explains why humid summer days often feel so heavy and why winter air, crisp and cool, feels much drier. As the water vapor drifts upward with the warm air, it enters cooler regions of the atmosphere. Remember what happens when warm air rises? It cools as it expands in the lower pressure of the higher altitudes. This is where things get interesting. Cool air can't hold as much water vapor as warm air, so as the air cools, it reaches a point where it becomes saturated with moisture. That point is called the dew point. Once the air has reached the dew point, the water vapor begins to condense. Molecules that were floating invisibly now cluster together, forming tiny droplets of liquid water, or if it's cold enough, ice crystals. But condensation doesn't just happen out of nowhere. Tiny particles in the air, dust, salt, or pollen, act as surfaces for the water vapor to cling to. These are called cloud condensation nuclei. Without them, water vapor might never condense into droplets large enough to form visible clouds. Imagine billions of droplets, each too small to feel on their own, gathering together. The result is the familiar sight of a fluffy white cloud floating high above. It's hard to believe that something so serene and quiet is born from ongoing, unseen change, the transformation of vapor into liquid, constantly at work in the sky. Humidity plays a central role in this process. You might already know it as the measure of moisture in the air, but there's more to it than just feeling sticky or dry. Meteorologists describe two kinds of humidity, absolute and relative. Absolute humidity measures the actual amount of water vapor present, while relative humidity compares how much water vapor is in the air to how much it could hold at that temperature. Warm air has a larger capacity for moisture, so the same amount of water vapor feels much more humid on a hot day than on a cool one. Once the relative humidity hits 100%, the air is saturated, and that's when condensation happens, creating the possibility of fog, dew, or clouds. Not all clouds are the same, though. The type of cloud depends on how the air is rising and how much moisture it carries. If the air is lifted gently, you get stratus clouds, flat gray blankets that can stretch across the sky, often bringing overcast conditions or light rain. But when air rises quickly, the clouds change dramatically. Rising air cools rapidly, causing the moisture to condense in larger amounts. This is how cumulus clouds are born. They're puffy, cotton-like forms towering over the horizon. When the atmosphere becomes really unstable, warm air rising fast, abundant moisture swirling upward, those same cumulus clouds can grow into giants. These are cumulonimbus clouds, the powerhouses behind thunderstorms. They reach immense heights, their tops forming the anvil shapes, often seen in photos of fierce weather. Within them, air currents cycle frantically up and down, building the energy that drives lightning, thunder, and sometimes even hail. For precipitation to fall from these clouds, the droplets need to grow large enough to overcome the resistance of the air holding them up. It happens when tiny droplets collide and stick together, a process called coalescence. As they gather into larger and larger drops, gravity eventually wins out, pulling them down as rain. In colder parts of the clouds, ice crystals might form instead of droplets. These crystals grow as water vapor freezes onto them, and when they're heavy enough, they fall, either as snowflakes, sleet, or even freezing rain, depending on the conditions they encounter on their way down. Snowflakes, as delicate as they look, are shaped by the unique temperature and humidity conditions they pass through during their descent. Some are intricate, with 6 symmetrical arms, while others are simpler and less recognizable. They're like nature's fingerprints. No two are exactly the same. Water vapor doesn't only create clouds and storms, it's also the driving force behind the entire water cycle. After precipitation falls, water collects in rivers, lakes, and oceans, only to be evaporated into the atmosphere again. This continuous cycle has been turning for billions of years, spreading life-giving rain across the planet and helping maintain balance. It's a perfect system, constantly working beneath our feet and above our heads. When you think about water vapor, it might not seem dramatic at first. After all, it's invisible. It doesn't rush through the air like wind or make noise like rain pounding on a roof. But don't let its quiet nature fool you. Water vapor is carrying energy into the atmosphere every second, setting the stage for massive events. A thunderstorm is in many ways the end result of uncountable amounts of water vapor rising from the surface, condensing, releasing heat, and building clouds that tower into the stratosphere. It connects the calm of a morning mist with the awesome power of a lightning storm. Without it, the atmosphere would lose its energy, and weather as we know it simply wouldn't exist. So the next time you see a cloud drifting lazily above, think about the invisible work behind it. That cloud started as water on the ground, maybe from a distant ocean, a local river, or even dew on the grass. It rose into the air as vapor, transformed into droplets, and found its way upward. It's a process so delicate and constant that it's easy to overlook, yet it shapes some of the most breathtaking phenomena in the world. But water vapor doesn't act alone. While it fuels clouds, rain, and storms, there are broader systems directing its movement and organizing its effects. High-pressure zones, low-pressure centers, and global wind patterns work together to transform all this energy and moisture into the weather patterns we recognize on maps and forecasts. These larger systems are the architects, shaping everything from gentle breezes to continent-spanning storms. To understand how all of this fits together, let's take a closer look at these patterns. The intricate designs that make our weather not just possible, but predictable, the patterns that shape our weather. What connects the gentle sigh of a breeze to the violent rush of a thunderstorm? Or the stillness of a summer morning to the chaos of a winter blizzard? While these events might seem isolated, they are deeply connected, part of a vast, coordinated system operating above our heads. At the heart of it all are large atmospheric patterns, high pressure and low pressure zones, convection cells, and circulating winds, woven together by the sun itself. Every gust of wind, every drop of rain begins with the same force, sunlight striking the earth unevenly. The planet is heated unevenly because of its curvature. At the equator, sunlight hits the surface more directly, delivering concentrated energy. Near the poles, sunlight arrives at a shallow angle, spreading its warmth over a larger area. This imbalance drives everything. Warm air near the equator rises, creating an area of lower pressure at the surface. Meanwhile, cooler, denser air from higher latitudes sinks, producing areas of higher pressure. Nature, always looking for balance, sets the stage for air to move from high-pressure zones into low-pressure zones. That simple flow of air is the foundation of global atmospheric movement. But the Earth's atmosphere doesn't stop at simple airflow. It organizes this motion into immense circulation systems called convection cells. There are 3 primary convection cells in each hemisphere of the planet: the Hadley cell near the equator, the Ferrel cell in the mid-latitudes, and the polar cell near the poles. Together, these cells create the flow of air that powers global wind patterns and weather systems. The Hadley cell dominates the tropics. It begins with warm air rising near the equator. After ascending, the air spreads poleward at high altitudes, cooling as it goes. Eventually, this cool air sinks around 30 degrees latitude, creating areas of high pressure. Deserts like the Sahara form under these descending air currents. This now dry air flows back toward the equator as the trade winds, completing the cycle. The Ferrel cell sits in the mid-latitudes, sandwiched between the Hadley and polar cells. Unlike its neighbors, which are more directly powered by temperature differences, the Ferrel cell is a kind of atmospheric bridge. It operates in reverse, with air flowing poleward at the surface and equatorward at higher altitudes. It's less stable than the Hadley or polar cells, but it plays a crucial role in mid-latitude weather. Here, you'll find the westerlies, winds that blow from west to east and steer much of the world's weather, especially in regions like North America and Europe. These winds often guide storms and pressure systems, giving the mid-latitudes the unpredictability they're so famous for. At the poles, the polar cell completes the trio. Here, the cold, dense air sinks and flows outward toward lower latitudes. This movement creates the polar easterlies, dry and frigid winds that blow from east to west, contributing to the bitter cold that defines these regions. While the polar cell doesn't have the drama of storms or the towering clouds of the tropics, it underscores the relentless effort of the atmosphere to redistribute heat across the planet. These 3 cells, repeating in both hemispheres, transform the Earth's uneven heating into a giant, interconnected conveyor belt of air. Zooming out, these cells are responsible for more than just winds. They carve the global weather zones that define our planet. Between the equator and about 30 degrees latitude, the tropics house lush rainforests and warm climates, thanks to the rising air and frequent rainfall of the Hadley cell. From 30 to 60 degrees latitude, in the mid-latitudes, you'll find temperate climates with more variable weather, influenced by the Ferrel cell and its changing winds. Beyond 60 degrees, in the high latitudes, the polar regions are dominated by cold, dry air and extreme conditions shaped by the polar cell. Each zone has its own rhythm, but together, they create a seamless, global system. The sun's energy doesn't just affect the air, it's also absorbed by the oceans, which play a hidden but powerful role in shaping these patterns. Oceans act like giant heat batteries, storing energy and releasing it slowly over time. This is why coastal regions often experience milder climates than areas farther inland. Warm currents, like the Gulf Stream, transfer heat from the tropics toward higher latitudes, just as the atmosphere does. These currents influence weather in profound ways, adding another layer of complexity to the patterns governing the planet. But there's more. The Earth's tilt, about 23.5 degrees, is what gives us seasons, and these seasons shift the atmospheric patterns. During the northern hemisphere's summer, for example, the sun's direct rays shift northward, warming the land and altering pressure systems. The trade winds, westerlies and polar easterlies, all shift slightly, following the heat. In the winter, the opposite happens. The sun's energy shifts south, cooling the northern hemisphere and changing wind patterns yet again. This ebb and flow of heat shapes how storms form and where they travel, adding an unpredictable edge to a system that otherwise works like clockwork. Within these massive systems, smaller features emerge, adding texture to global weather. High-pressure zones where air sinks bring sunny skies and calm conditions. Low-pressure zones where air rises create clouds and stormy weather. These zones change constantly, driven by the constant heating and cooling of the Earth. High-pressure areas might settle over a region for days, bringing a streak of dry, sunny weather. Or a low-pressure system might sweep in, bringing gusty winds and heavy rain. These features form the day-to-day weather we're so familiar with, but they're always connected to the larger patterns at work. One of the most well-known examples of these interactions is the jet stream. High above the surface, these narrow bands of fast-moving air form along the boundaries between major air masses, like where the warm tropics meet the cooler mid-latitudes. The jet stream isn't just a wind, it's a key player in steering weather systems. It can pull moist air into an area, triggering storms, or block systems from moving, leaving a region stuck in a dry spell or cold snap. The jet stream's position and strength often decide how extreme the weather in a particular region will be. Even the chaotic energy of a storm isn't without its connection to these larger patterns. Take a hurricane, for instance. These powerful storms are born in the tropics, where warm ocean water heats the air above, causing it to rise and create a low-pressure center. The spinning of the Earth, the Coriolis effect, helps shape the storm, turning rising air into the familiar, spiraling structure of a hurricane. Once formed, the paths these storms follow are often guided by the trade winds or the boundaries of the westerlies. A storm's life, from its creation to its eventual dissipation, is shaped by the global systems moving around it. What's astonishing is how predictable this all is, even in its apparent chaos. Storms may seem random, but they follow the rules set by the larger patterns. Winds may swirl unpredictably in one place, yet trace graceful, consistent arcs on a global scale. Despite its complexity, the atmosphere operates with an underlying order, its patterns governed by the physics of heat, air, and rotation. Even the most violent storms and the gentlest breezes are part of the same vast system, endlessly moving heat and air across the globe. As we follow these patterns closer to the surface, we start to see moments where they collide. The meeting of warm, moist air with cold, dry air can spark dramatic changes. This clash creates the type of weather that commands attention: thunderstorms, tornadoes, and rapid shifts in temperature. These are moments when the atmosphere seems to come alive, showcasing the tension between the orderly patterns above and the chaos they create below. Understanding how these fronts form and what happens when they meet is key to unlocking the full power of the atmosphere. Let's take a closer look at these dramatic moments where warm and cold air collide and storms are born.